trig heighting with a height range greater than 100 metres. As part of our heighting exercises that we were doing, we are required to cite and record observations for vertical height for measurements less than 100 metres and less than 500 metres. Now here in Tauranga, we're not really blessed with too many opportunities to observe trigs or such like at such a big range of height. So it became very difficult exercise to try and organise something to do this. So we had to think of a way how we could still achieve the same goals but doing it a little differently. So what I came up with was what I call reverse engineering. So what we're going to do is we're going to start with two known heights from two known points and work backwards to try and calculate what the observations might have been from those points under particular circumstances. Now, doing something forwards sometimes be quite difficult, but if it's difficult going forwards, it's twice as difficult going back. So the theory here is that if we can do this or reverse engineer it, or do it in reverse, that we're going to know our topic way better. So the question was, and let's not exclude the possibility that some of us may be able to observe and reduce a set of observations between two stations with known height. You may be able to do that. You may be in a situation where you can do that. But if you can't, you can manufacture a set of field notes, and I say that with difficulty because surveyors are not allowed to do that. So I don't recommend that in any circumstances except in this circumstances for the purposes of exercises and training. We're going to try and manufacture a set of field notes between the stations and then reduce them to show they are correct. Now, the two stations I have chosen are two that I am very familiar with, and that they are the Ngaruawahia Fundamental and Tapri Mountain, which are very close to my home and my heart, as it appears, in Ngaruawahia. So the first thing that we want to do is what I've done is gone to the geodetic database and got the information for this, for the trig here, the Ngaruawahia Fundamental. Now we're going to be working in Mount Eden circuit coordinates, so we can see here that we've got the coordinates 7 down in here, Mount Eden circuit coordinates, and we'll note that these are in sort of in New Zealand geodetic datum 2000 terms and they're fifth order coordinates. So they're reasonably accurate. It's a really substantial mark down by the band rotunda at the point. We'll also note here that it has heights in both Maurieo datum and Port Waikato datum, and the heights on this mark are to first order vertical. So that's a pretty substantial and significant mark. And the next mark that I was going to observe too is Tapri Mountain, a very significant mark in the area, and one that most people, or a lot of people, would have driven by. So it's a significant third order trig. We see here it's got coordinates, Mount Eden circuit coordinates. They're the ones we're going to be using, and it's got heights on it in terms of both Maurieo and a mean sea level. So we're going to use the Maurieo height, which is a third order vertical height. Just notice that it's given to 2 decimal places. So not incredibly accurate as with the first order, but probably accurate enough for us to get some good value out of the exercise. Just a little bit of details here about the mark. It's a 4 metre high beacon, so it's quite a significant beacon, and as far as I'm aware, and we can see it from the Ngaruawahia Fundamental, but for the purposes of this exercise that's not absolutely required, an absolute requirement. So here we go. So I've put down our details, which I've copied, as I say, from the geodetic database, the LIN site, and all those details that you saw on it. So the next thing we want to do is we're calculating the distance between them. In some cases, when we do these things, we are able to measure, but in this case, we're just going to do a one-way trigonometrical observation, presumably or assumedly from the Ngaruawahia fundamental to Tapri. And so we need to calculate the distance. But just before we do that, looking down here, I see that there's a further little piece of information that we need, and that is the information that, again, from the geodetic database, and these are the details of the trig on Mount Tapri. So here we are, we've got some of the details. It tells us about the details, about the mark, how we can get there. But most importantly, it gives us some details of the beacon on there. And in particular, I'm using this distance here, the 3.49, which is the height at the top of the vanes. And that's where we will be observing to with our virtual theodolite from the Ngaruawahia fundamental. So just making you aware of that. Get rid of that, and here we are back to the thing. So the next thing to do is to calculate our the distance between the two marks. Now we have to be very careful here because in the Mount Eden circuit, as you would have seen from the details there, that we have this 0.999 scale factor. So that has quite a significant effect on distances, particularly the ellipsoidal distances, which is the actual distance that we measure between the 2 points. If we were to just take out a straight join without reference to the scale factor between the coordinates of the two marks, we would get a plane distance which hasn't taken account for the scale factor, and would hopefully in all likelihood be this 7500.683. Now note all of these distances here have been reduced to sea level. So what I recommend here for working out this vector is that you use some sort of a survey software to do so. So what I've done here is I've just got a screenshot of the survey software, just illustrating the particular reduction that we did. And here it is. Here's a map. I've plotted the 2 points showing the Ngaruawahia fundamental and Tapri, and I've sort of done it in a traverse sheet situation. So we've put in 1 here, the Ngaruawahia fundamental, and 2 the endpoint, which is Tapri Mountain, and the coordinates there. And what we've done is, using that traverse sheet, we've got a bearing of 28 degrees 39.74 seconds for a distance of 7501.317. Note that's an elliptical distance. The particular software also has another means of measuring it, using a particular geodetic type measurement, or measuring ellipsoidal distances, and again it shows it here. It gives the bearing, the plane bearing, which is 28 there, and the plane distance, which is 750683, which I've recorded. And here we have the elliptical distance. Note down here the scale factor, which is the 0.9999, very close to that. So and you can see we've sort of measured it and done it both ways, and everything checks out. So we now know that we have a good elliptical distance, 7501.317. Okay, so let's go back now to our calculation. And here is all that information recorded here. I've just worked out the difference in height between the two heights. So that's 273296 is just 287.52 minus 14.2239. I'm tending to work to 3 decimal places where I can, but that Right, here we are back again, and just going to look at sea level correction next. I should point out that the distance that we have determined here is the actual calculated distance. I haven't considered any of the corrections to a measured distance that might apply. So this is the reduced ellipsoid distance that you would result after you had reduced a measurement with EDM or what have you. So because we're operating at height here, we do need to consider that the distance we're measuring or that we're observing, the slope distance we're observing along, is in fact measured at height. So we have to allow for sea level correction. So just the first thing I've done here is to calculate the average height, which is what we do for sea level correction. So that's the height at the fundamental plus the height at Tapri Mountain, added together, divided by 2. Now our formula for sea level correction is 15.69 times the average height times the distance times 10 to the negative 8. And that comes to 0.178 meters. So we must add that on to our height that we determined up here, 7501.317, and our height, or our distance at the height, or unreduced to sea level, would be 7501.4946. Remains to be seen in this instance as to whether that would be significant in the calculation of the height difference, but for accuracy's sake I've done it here. The next thing we then need to move on and consider is curvature and refraction, what effect this is going to have. Now the accurate formula for curvature and refraction, which you'll find in amongst your notes, particularly Paul Denise's notes, is stated here, 1 minus k, where k is the coefficient of refraction, and the one that's commonly used, 0.14, times in s squared, where s is our, as I say, our distance and height that we've worked out there, 7501.495 squared, and then divided by 2 times the radius or of the diameter of the Earth, or radius, Earth radius, I suspect, and that is 6374000 meters. And I emphasize the meters because it's given in the books as 6374 kilometers, but for the purposes of this formula it needs to be in terms of meters. So when we work that out, we get a curvature and refraction correction of 3.796. Now normally the curvature and refraction correction, of course, is added on to in normal circumstances, but in this case, because we're working backwards, we are subtracting it. Same goes for the target height. Normally, or the way that I look at it, is I start at the mark, add the instrument height, then the difference in height, and then subtract the target height. So I'm doing the reverse here. We're reverse engineering. So in this case here, we're taking off the target height, which is 3.49, adding on the target height, which is 3.49, whereas normally we would take it off. And here the instrument height, we're subtracting that, whereas normally we would add it. And that gives us a height, an uncorrected difference in height, or the difference in height, which would be uncorrected. This one being the reduced one of 271.190. Well, I've called it HUNC, meaning the uncorrected difference in height. So from that, we now are in a position where we can calculate the vertical angle. And the vertical angle can be determined as tan to the negative 1 or of the uncorrected height divided by the distance at height. And if we do these in the calculator, just remembering that that's 271.190 divided by 7501.4946, and taking tan to the negative 1 of that, we get 0.0361514. Now I did a little bit of investigation here to see how many decimal places. I've done this calculation in an Excel spreadsheet to see how many decimal places this calculation needed to be to get the sort of required accuracy. And I determined that it needed to be at about 7 decimal places. This is something, if you do this in a spreadsheet, that you can possibly do yourself. I just put in different values in here and converted them to see how things panned out. In fact, I actually did it on a scientific calculator, working out the different ones that I needed to show to get a reasonable angle. I believe that I've got the angle correct to that first decimal place of a second there, which is, seeing that we're possibly only observing to the nearest second, it's pretty reasonable sort of accuracy. So there we are, we've determined the vertical angle like so. Now what would this translate into as a zenith distance? Well, as we know, this is a rise or elevation, so the zenith distance would be less than 90. So we take our 2 degrees 0413.5 off 90, which gives us 87.55, 46.5. And then I thought, just to make things more interesting, a bit more challenging, I thought, well, usually we encounter an index error, so I just arbitrarily said for this particular observation the index error was 8 seconds. You might like to choose one yourself, but seldom is it ever 0. So that gave us an index error, which leads us to a set of observations here. Face left would be 87.55, 54.5, so that's 46.5 plus our 8 seconds, and our face right would be, again, what I did was I determined it because the index error would be 8, so it would apply equally to both. So I added it so that it would add to 360 degrees 0016, so that's 272.0421.5 seconds. Now you can see that we've calculated a vertical angle up above, so of 2 degrees 0413.5, and you can see our 0421.5. If you take 8 off that, of course it gives you the 13.5. So that's a sort of bit of check as we're going along. Okay, so there we are. We've got our observations there. So let's check. Let's just check that we've got them right by just running them through them in the normal course of time. So here we are. We've got our adjusted zenith distance. In this case, adjusted it for index error of 87.55, 46.5. Which translates to a vertical angle of 20413.5, which again agrees with what we've got up above. If we take the tan of that and then we multiply it by our distance that we get here, that we determined above, which would be unchanged, would be the distance at height. Like so, we get a difference in height of 271.189, which I think agrees within about a millimetre of what we determined further up the way here, 271.190. So we're out about a mil. That's resulting from rounding errors and calculating in various calculators and things like that. So we add on our instrument height this time rather than the reverse, and we subtract our target height, and then we, because we're at elevation, we add our curvature and refraction, like so, and that gives us our height difference of 273,295, which we then add to our height for Ngaruawahia, and that gives us our final height for Tapri Mountain of 287.52, which I think we'll find is in general agreement with what we started with. So there we are. There we have a reverse engineered calculation which shows people, or is good evidence, that we are fairly familiar with this operation of calculating trig heighting with the height range, like so. So what I suggest you do yourselves is to provide your own evidence, is that you choose perhaps 2 marks that you are familiar with that have a height range of greater than 100 metres, and come up with a calculation of your own.